Okay. ¿Tanco la puerta o? Okay. So let's start. Good morning to everyone, thanks for coming. I'm Patrick Sánchez, and today I'm defending my master thesis titled Financial Contagion in the Interbank Market, and supervised by Pere Collet. The structure of the thesis will follow 5 main points. First, I will introduce and mention the importance of financial contagion, and in particular the interbank market. Then I will proceed to introduce the A-Kapadia model. We will add some kinds of heterogeneities into the model. Then we will couple the interbank market with an external market. And finally, I will conclude with conclusions and outlook to see the state of the art. So to capture your attention, let me start with a simple question. Why should we mind about financial contagion? Because it sounds a bit esoteric. And the best answer I can give you is this: the crisis of 2008, the Great Recession. It was strictly a financial crisis, meaning that it was not due to the lack of resources or political issues. That started in 2008 in the USA due to the subprime mortgages, in which banks gave mortgages to people that had no money, no assets, no job, and no income, the so-called ninjas. The crisis rapidly spread through the entire world, and the worrisome part is that economists thought that these kind of financial contagions were not, the system was robust enough to not happen, these kinds of contagions. So they think that this couldn't happen, and then they found this catastrophic crisis. This crisis spread in several channels, but mainly it happened in the interbank market. So we want to focus on this system. Okay? So let me explain very quickly how it's about the interbank market. We have here a simple sketch with 4 banks, A, B, C, D. As you can see, banks A and bank B has less income in blue than outcome in red, so that they are borrowers, they need to borrow money. And on the other hand, we have banks C and D, that is the other way around. Okay? Moreover, we have customers, like you and me, and there are some regulatory institutions, as central banks, that aims to stabilize the system. So what happens when, for example, bank B cannot pay? Well, we're in trouble, okay? Because if the bank cannot repay the loans, some banks may lose this money, and eventually they may not return their own debts. So the system can get paralyzed, and then, of course, the state comes, changes the rules of the game, and so on, okay? So before we start with the A-Kapadia model, we need to understand how a bank behaves. Banks essentially have 2 kinds of elements, assets and liabilities. Assets are income, so positive money, and assets are debts to pay, so negative money, more or less. Assets are composed at the same time into 2 parts: external assets, which are not from the interbank market, and that are mainly illiquid, meaning that you cannot sell these assets to obtain the full amount of the value. You can make it, but obtaining less amount and in different time scales. Maybe you obtain it in certain days, okay? While there are interbank assets that are more or less daily, so liquids, that if you observe this, there's a new parameter phi that reflects the fraction of borrowers that are in default. Okay? So 1 minus phi is the borrowers that are alive, so that they can pay. Okay? Of course, for the external, it's the same. The parameter is Q, called the fire sell multiplier, and reflects this when you sell and you do not obtain the full amount. For the liabilities, we have the reciprocal ones, external and interbank liabilities, and moreover, we have deposits from customers that withdraw money. And as you can see, there's a difference between assets and liabilities that is called equity. Okay? In principle, banks should have positive equity, as you can imagine. Okay, all this can be summarized in this simple equation, which is the equation for the equity of the bank. And when the bank has positive equity, it's solvent, so it's working properly. But when the equity is negative or 0, it's in default, so it has problems. Okay? But we're still missing an important point of how a bank behaves, and are financial regulators, okay? In this case, represented by Mario Draghi. And they make some requirements to banks. Okay? The most important one is the capital buffer. They force all banks to have at least a certain amount of their assets as difference from assets and liabilities. So a positive equity fixed, greater than or equal to a certain amount that we will fix into 4%, which is commonly observed in the literature. And moreover, notice that since we need to know the fraction of interbank and external assets, we need to put some fraction of them. And we're taking, in particular, an 80% of external assets and a 16% of interbank assets. Okay, so let's introduce now the A-Kapadia model for financial contagion with a network model. This is a simple sketch with banks A, B, and C. Let's focus, for example, in bank A. As you can observe, there's a liability of bank A to bank C, another one from bank A to bank B, and at the same time, bank A has assets from B. And you may wonder why there are these kind of loops. This happens because in some day, a bank may need money, but the next day, it may have excess of money. So they can have mutual loans at the same time, and in fact, the maturity, this is the period in which you need to pay, may be different. So that's why we have this kind of loops here. Of course, they can be translated easily into network terms. And the A-Kapadia model then follows the following steps. First, we initialize the system. First, we generate a directed graph. Then we assign a certain size to each bank. We can make them equal or different. We define the fraction of interbank external assets and equity, as we did before. And then we distribute the interbank assets among our neighbors uniformly by now. Okay? And then we start with the dynamics, with the cascade of defaults. We start by a default of a random bank. Then all the out neighbors, these liabilities, lose the whole amount of the loan, which is a zero recovery assumption, which doesn't change so much the evolution of the system. And finally, we compute the new defaults. If there are new defaults, we start again with step 5, and again, until no new defaults there, okay? And we will focus on the moment in which dynamics starts and there's a systemic failure, defined by the moment in which at least 5% of the total banks are in default. This is what we're going to study. So results are shown here for another Renyi graph. In blue, you can observe the probability of contagion, and in red, the extent. Okay? Results are for 1,000 banks and 1,000 independent simulations. These are the typical values that we'll use for all the simulations. What do we observe? First, there's a finite window of connectivities in which the probability is non-zero. You may ask why there's this little tail, but this is because of finite size effects. If I take a larger system, the decay is really sharp. Moreover, we observe that in orange, the extent is continuously increasing, monotonously increasing, so that the more connected the network, the more banks fall if there's a systemic failure. And the combination of these two properties is commonly known in the economic literature as robust yet fragile property. So, additional studies are doing selective attacks on the left, attacking a bank with a single liability, with a lot of liabilities or at random. And since the network is completely random, we observe the same result. So, and on the right, we buy the capital buffer. And as you can imagine, the larger the capital buffer, the more they can absorb from other banks. So the lower, in green, the probability of contagion. So no surprising at all. And up to here, we've been reproducing the A-Kapadia model. No? Let's now extend the model and introduce some realism. And in particular, I will introduce heterogeneities in the model. First, I will consider a different network, not just random Renyi, because the empirical studies point out that the interbank market follows a scale-free network, okay, that typically present hubs. So in our terms, this means that these banks in black can distribute their risk, their loans, their interbank assets among more neighbors. So if this, for example, this neighbor falls, the shock is very little for the hub, for the big bank, okay? This is a reference for how to construct indirected networks varying the in and out exponent, if you can see it. And the results are the following one. In blue for the Renyi, in orange for scale-free, okay? What do we observe? First, there's a very big difference in the maximum of probability contagion due to the fact that now there are banks very connected that distribute risk and they are robust to contagion. More things, the extent of contagion is roughly the same, more or less the same. So the robust yet fragile property, a low probability of contagion, while the extent is very high, is preserved. There's a long tail of connectivities that present a non-zero probability of contagion, which means that the risk diversification is not working properly. And this is because when we add links in a scale-free networks, those links are mainly put on highly connected nodes. So we need more and more links until poorly connected nodes diversify enough to not suffer a big shock, okay? So to resist the contagion. In the economic literature, again, they have fancy concepts, and this is known as twin connected to fail, distributing your interbank assets a lot. Let's do a selective attack to see what happens. And we observe that attacking a bank with a single liability in green reduces the probability of contagion. And this is because if I have only one liability, at most I can kill the second, my neighbor, the following neighbor, no? And this neighbor is very probable to be a hub that resists financial contagion. So it's more or less logical that probability of contagion is less. What we observe when we attack a bank with a lot of liabilities. For lower connectivities, we observe that this attack is catastrophic. It enhances instability. While for larger connectivities, attacking a bank with a lot of liabilities is less effective than attacking a random bank. Okay, let's now introduce another kind of heterogeneities. Okay, there's a lot of evidences in empirical literature pointing in the direction that wealth distributions follow a Power law, and in particular with an exponent between 2 and 3. So, of course, banks are not an exception, and we will make banks of different sizes following a Power law, particularly with 2.5 of the exponent. And since now banks have different sizes, they can distribute the interbank loans, assets, proportionally to the size of the neighbors. So if a neighbor is bigger, have more money, I put more loan there because it's more robust to contagion, okay, following this expression. So it's a direct proportionality. What we observe, in blue we have the homogeneous case, in red the heterogeneous case, and we do the simulation for another Rényi graph to not confuse the results with the scale-free topology, okay? First, there's a long tail of probabilities that are not zero, again, as in the scale-free network. That means, again, that risk diversification is mitigated. And this is because since now we have big banks that can absorb shocks, there's not a point in which I increase the risk diversification and the financial contagion stops, okay? So big banks act they distribute the financial shock. Moreover, the maximum of the probability of contagion is lower in the heterogeneous case. And this is because big banks can absorb bigger shocks, so that they act somehow as firewalls for the system. And again, another fancy concept is this one. The big banks can absorb these shocks, and it's called as too big to fail. Okay? Let's do, again, a selected attack. What do we observe? Here, for lower connectivities, attacking a bank with a lot of liabilities, so very connected, increases instability. No? Probability contagion is very high. While for more or less medium connectivities, it's less effective than attacking a random bank, as we saw before. The problem is that attacking a big bank, so a rich bank, it's really catastrophic for the system, because for connectivities 2 or larger than 2, the contagion probability it's monotonously increasing, so it's very important. So the message would be better to reach than to be famous. Not like this, but of course the idea is that at least for financial stability, it's better to be a big bank than to have a lot of connections and diversify a lot. Okay. Up to here, we've been introducing heterogeneities, but what happens with effects that are not common from the interbank market, but from the outside? We're going to couple our interbank market with a private sector firms, which are more or less the most important factor. And let's start with the simplest case, in which we only have one firm, one big firm. Okay? All banks have a certain amount of money put on this company, a certain investment. This investment, this parameter C, is the fraction of total assets invested in this company. And there's a second parameter, phi, which is related to the valuation ratio of this company. So how the value of the company is decreased when a certain investor wants to retire the investment. Okay? So this fire sales mechanism, when banks try to sell these investments, are mainly a mechanism to obtain liquidity, because if a bank is in default, it keeps in default, but it can obtain liquidity to try to pay at least the debts. Okay, so that's why they do fire sales. Each time a bank sells a certain amount of the investment, the company gets evaluated, and this evaluation, since it's related to investments, make some banks that have, in this case, all of them, because they have invested in the company, they lose a part of their assets. And of course, they lose the amount they have, the C, product A, and the depreciation value, the valuation of the company. Okay? What do we observe? In blue, we can observe the system without firms, and in orange, with a single firm. Okay? With these parameters and these conditions, which are moved a little bit. Okay, sorry. What we observe? The maximum probability of contagion increases, in general, and moreover, the contagion window widens. And, as you can see, there's no threshold at which the probability of contagion is 0. So there's a smooth decayment. And this is because we have added an additional channel of contagion. We have direct contagion due to other banks that cannot pay. And we have the devaluation of the company. So each time there's a default, the devaluation of the company happens, and then banks lose a certain amount of their value. And again, banks that would resist a direct contagion may default just because of the devaluation. Okay, this is an in-depth study of this introduction of a company. In the left, I've studied what happens when varying C and phi for an Edorreni graph with average degree of 7.5. That, if you think about this, should not present probability of contagion. Okay, so now, as you can see, it does. And first, we observed that both cases, varying C and phi, give the same result, very similar. Okay, and it's a sigmoid-like function with some plateaus that can be explained, but I have no time now. If you want to answer them in the question round. But the point is that they are very similar. And they are very similar because if you think about the devaluation, banks depreciate as a product C phi. So in fact, there are no difference between C and phi. They are somehow a product that define a new control parameter. So on the right, you can observe what happens when we increase this control parameter C phi. Okay? And the larger the loss of the value of banks, the larger probability of contagion, as you can imagine. So not very surprising, but at least we have studied what happens when we increase it. Notice that it increases a lot when we are far from 0.006. So let's move to the case in which we have several companies. The problem now is that we need to couple the interbank market with the private sector, and we need to do it in a proper way. And I decided to do it in this way. We ask Bank I invests in firm J. With certain probability P invest, it does. With probability 1 minus P invest, it does not. Okay? So to clarify this, let me put a very simple example. If we have 1,000 banks and 100 firms, and the probability of invest is 0.3, typically each bank has invested in 30 different companies because the probability is 0.3 product 100 firms. Okay? So this is clear. What happens with the fire sales in this case? Let's, for example, kill Bank 2. So since it has investments in company 1 and in company 3, those companies get devaluated, okay, so they decrease their value. And then, since Bank 1 has investments in company 1 and Bank 3 in company 3, Bank 1 and Bank 3 decrease their value, their equity. Okay? If some of them get in default, this eventually may lead to other depreciation of companies and again and again. So this mechanism amplifies the initial shock. And here we have the results, comparing the case with one firm in green and with several firms and different probabilities to invest. Okay? Again, the topology is Edorreni, and this is very important. We've made all the companies the same, the same kind of company, let's say, because the devaluation ratio is the same, 0.3. Okay, so they behave in the same way. Moreover, we have fixed the amount of assets that banks have in companies, so that they put a 2% of their total assets, irrespective if they have an investment in a single company or in 5. Okay? They put the same amount in total. Notice that the limit in which P invest is equal to 1 corresponds to all banks investing on all firms. But all firms behave as similar because they have the same devaluation ratio. So essentially, it's the same that having only one firm. So this limit is the same than having only one firm. We observe that the additional channel enhances instability, as you can see here. And moreover, the important thing is that the higher the probability to invest, the higher the probability of contagion, because you are exposed to the defaults of more banks and then the devaluation of more firms. Again, there's a long tail of connectivities as in the single firm case. Okay? So let's end up with the conclusion and look. And we've seen that risk diversification does not always increase the stability of the system. So this thing that economists trust, maybe take carefully. The robust yet fragile property, let's say. Heterogeneities eliminate the connectivity threshold because now there's a smooth tail. Seems to be that high wealth is more important than high connectivity in stability terms. Moreover, the external market amplifies the initial shocks, and there's strong dependence on certain parameters. So we need to be careful when studying theoretical studies and watching new parameters inside. Let me speak a little bit about the state of the art. We have only considered what happens when a bank is in default and cannot pay, which I'll commonly call first round effects. But what happens, for example, if we introduce time evolution so that there are several loans each day, and they can receive several shocks. This is, I think that it's being done. And there's a third, let's say, procedure or mechanism, which is called accounting. That is, if a bank thinks that another one can be in default, maybe I just don't let them money. And this can be amplified and have several consequences. More other things that have been doing is to consider the real decision making of bank when negotiating and the partial information they have. And let me end up saying that adding parameters as crazy is not recommended and is nonsense if we do not understand the real fundamental mechanisms in the model. Okay. So here's some relevant bibliography, and thank you for your attention. So if there are any questions, now's the time.
Thanks. Well, we can start then the round of questions.
Well, first, thanks a lot for the presentation, for the thesis. I really liked reading it, and I think you also did a very good job in introducing this relatively complicated topic, and now I know a bit more about the interbank market. And, so not just the research you did, but also the exposition.
Thank you.
That's what I could also hear. Yeah, let's discuss this a bit. So you decided to completely